polypropylene microreactor with integrated magnetic steering and electrospray ionization functions for mass spectrometric chemical reaction monitoring.
That was a long title, right? Ladies and gentlemen, my name is Gian Mario Scotti. Close the door because it makes me nervous. I'm a postdoc at the University of Helsinki Faculty of Pharmacy, and I work with Sofia Nilsson, Dr. Markus Haapala, and Professor Tapio Kotiaho. As you can see, I have abbreviated the title and also the presentation a little bit. I hope to be able to tell the story of an interesting microreactor, 3D printed from polypropylene, and which is used for chemical reaction monitoring by mass spectrometry. In recent years, 3D printing technologies have been used more and more by the microfluidics community. There are several reasons, but the main reason is the reduced cost compared to traditional microfabrication technologies. There are other benefits, such as new materials which are not traditionally used in microfabrication, in traditional microfabrication. And there is also the benefit of rapid prototyping. Let's get familiar with this microreactor. From these schematic diagrams, you see that this microreactor is composed of three main components. There is the polypropylene shell. Then we have a Teflon-coated steering bar. And we have a nanospray needle, which is used for electrospray ionization of the analytes. So that is effectively our ion source. The way that we embed or integrate these components together is what I will explain a little bit later. Now, just a few words about rapid prototyping. This has been a boom in this research. Like in every research that uses 3D printing technologies, people do, and in any case, they should take advantage of rapid prototyping. So what happens with 3D printing is that you have an idea in your mind, and if you have a good 3D imagination, then you sit at the computer, and within, let's say, 1 or 2 hours, you have a design. And then you can print it, and in a couple of hours, you can test it. So basically, from idea to finished prototype, there is just hours. Then, depending on your testing methodologies, there is some time. But basically, it is imaginable that the design and testing cycle could be something between hours and days. So you can rapidly go to back to the design board, drawing board, or in this case, a CAD computer, and modify your design. So because of rapid prototyping in 3D printing technologies, you can afford to be brave or crazy. You can afford to do it, because the worst that can happen is that you lost maybe a few hours or 1 day, and no project will be, will explode because of just a few hours of delay. So you can afford to do really crazy designs, which what actually nature does, if you think about it. Nature starts with crazy designs, and a lot of those die out, and then the stable forms and the best designs survive. So in a Darwinian evolutionary fashion, that's how this microreactor was also developed. These are just some of the intermediate steps that I went through. There have been many more. So you can believe that the design we have settled on was really the best possible in the world. Anyway, the 3D printing technology that we used in this project is called fused deposition modeling, which works in the following way. You have these spools of a polymer filament. In this case, there are 2 spools, but one is active. And the filament is either pulled or pushed into this heated nozzle. The nozzle then melts and extrudes the polymer through it and deposits it in an XY layer. The first layer is deposited on this build platform, and we hope that adhesion is good. This is where the first problems could appear, bad adhesion. Okay, then when you finish this first layer, the next layer is deposited on top, and so on and so on. And we took full advantage of this process, because what we did is we printed several layers of our microreactor. Then we stopped the printing, we inserted the nanospray needle, and we resumed printing. Then after several more layers, we stopped again, we inserted the Teflon-coated stir bar, and then we continued printing, and then we finished printing. In this way, we managed to embed these two foreign components in our polypropylene microreactor. My professor calls it chip, so. Anyway, why polypropylene? So it turns out that polypropylene is one of the most inert polymers that can be used with fused deposition modeling. In fact, I think it is the most inert polymer that works with this fabrication technology. Teflon would be better, but Teflon cannot be injection molded, so it's not suitable for FDM. There are 3D printing technologies that do use Teflon, but those technologies are not suitable for insertion of things. These little tricks, they only work with FDM. So yeah, polypropylene, it's inert against most organic solvents that are typically used in chemical engineering or chemical research at room temperature and even hot solvents, and it's inert towards most inorganic acids and alkaline solutions. In fact, polypropylene is even inert against boiling aqua regia. I know because I tried, and so what I had is I had this little holder in which I would put my wafers to be etched in aqua regia, and the stainless steel screws just fell out because they were etched away. So the only material could replace them successfully were 3D printed polypropylene screws. Okay, so here are a couple of these 3D printed microreactors next to a €1 coin. The only difference is the color of the polypropylene. Both of them work. Okay, as you can see, this project took full advantage of 3D printing technologies, thus drastically decreasing the cost, because we basically built our experimental tools by 3D printing. This holder, this jig in which the microreactor is inserted, is 3D printed. And what we use as an actuator for the stir bar is a very cheap computer fan on which two magnets have been glued. So basically, no price, zero price except for just a little bit of thinking. Here you can see the microreactor attached to a mass spectrometer. This is an Agilent ion trap. And now let's see. The reaction that we have analyzed, among others, is a fairly complex Diels-Alder reaction. I don't know if you're familiar with it, I hope not, so I don't have to explain too much. But it's complex because there are actually two Diels-Alder reactions going on. One is an inverse electron demand, and the other one is a reverse Diels-Alder reaction at the end. And that's how we get this final product. Don't ask me the name, I don't know. Anyway, so let's, this is a simplified scheme of the reaction, in which the main actors are highlighted in 3 different colors, the final product being blue. So let's see what we obtain. This is a mass spectrum of the analytes at a certain point in time in the reaction. And this is an extracted ion chromatogram of our 3 actors. And as you can see, the final product gradually increases with time, which is what you would expect from a chemical reaction, right? So we were very satisfied with what we obtained. Actually, this is a very, very abbreviated presentation of all the results we had in this research, because we analyzed with MSMS or MSMS even a lot of these side products, a lot of the intermediates. So we had a lot of fragmentation schemes that we produced from this, which we will publish hopefully soon. And so I'm not going to tell you about that, but this proved to be a very, very good microreactor for mass spectrometric analysis. Okay, just a few words about mixing efficiency measurements. So my intention was to quantify the mixing efficiency, because I was very proud of the fact that we managed also to insert the Teflon-coated steel bar. So my idea was to use these two species as the ones that we infuse in the microreactor. So this is testosterone and deuterium-marked testosterone. So why I chose these species? It's because the intensity of the peaks of these two species should be identical, or at least very, very similar if the concentrations are similar. In other words, the intensity of the peaks of these two species is directly proportional to the concentrations of these analytes. Of course, it also helps that they don't chemically interact. And it also helps that their diffusion constant is practically identical. And with these experiments, we have seen that the mixing efficiency is extremely high. In fact, in the first few seconds, we have almost complete mixing. The only problem is that with the electrospray ionization, you can only transfer very small amounts of analytes to the mass spectrometer at once. So whatever quantities of analytes have remain in the nanospray needle or around it, those would cause us to underestimate this efficiency. And so, in conclusion, so we made a nice little microreactor using 3D printing technologies, meaning it cost us next to nothing. We chose polypropylene because it's one of the most inert materials available for 3D printing. We used rapid prototyping a lot. And yeah, we have successfully analyzed a Diels-Alder reaction which produced a lot of fragmentation schemes and other interesting, chemically interesting results. And with this, I would like to invite you to ask me some questions. Yes, sir.
PP is not a very popular material for FDM, like ABS.
Sorry, polypropylene.
Yes.
Yes, it's not. Luckily for us, yay. But unfortunately, I have seen now that you can actually buy it relatively easily. There's traditional companies that sell polypropylene, that sell filaments. You know, the normal traditional companies. Now they have started selling it. Because back then when we started this, I actually really had to hunt for this. It wasn't easy to find polypropylene filament. But now, unfortunately, it's more available. Unfortunately, I'm just being a little bit sarcastic here. But yeah, so if we don't publish this very soon, then the others will jump on this bandwagon, I believe. Because this material is really excellent for microreactors or for microfluidic experiments. Because there is no better filament at the moment for that.
So the question I had, didn't you have a problem with warping?
We solved that. We had many problems, of course, and we solved that.
Because that's what you expect from polypropylene.